Hi everyone, that's week 5. We were moving to module 5, Big Data Applications. In the other word, you already finished 4 weeks out of the 16-week semester. We are quarterly finished this semester. Congratulations. So now we already have our static array and the dynamic array header file. We were using that header file you implement in the past couple weeks. We will start solving our one series big data application assignment. So since we say module 5 is big data application, what is big data? I believe you heard about that a lot of time. We have fast internet search. We have our AI control. That's all because we have amount of data we can process quickly. So here, the big data, we may not really use that at all from our prior courses, because sometimes the big data actually doesn't mean only have 1,000 data, not only mean you only have few hundred data. Actually, we are talking about 1 million or 1 billion data. So how can we process that fast? Before we start talking about the big data, we will also review a little bit about the big O runtime efficiency we talked about beginning in this semester. So then we will talk about one big data set is our DVC scheduling. You will process a text file that contains all the DVC courses from 2000. So far we are in 2020. That's about 90,000 courses section being offered in DVC. So that's one of our serious programming assignment we need to continue. So this week you will do the DVC scheduling version 1. So this assignment we will approach in different algorithm. So this week actually your runtime will be a little slow. So then later on when we learn more data structure, then you will see how we will improve the same problem we solve using the DVC text file, but the runtime will be much more faster in the future assignment. But the first thing, let's talk about our big data. So the big data actually is a big issue in the data structure. The reason why we have data structure, that's because when we try to access the data, we have different reasons how we want to modify or copy or delete our data. So according to the nature of your data, we need to find a most efficient way to store the data. So that's why we have different data structure. So one thing is, let's talk about big O here. Remember in first week, I kind of quickly to talk about what is the definition for big O. So for now, you just need to know we're using the big O notation to evaluate the algorithm runtime. So depends on how you implement your code to solve the problem. We have the big O notation to represent the average runtime efficiency. So the most popular one here, I will show you two kind of big O runtime. The first one is big O n. So the other one is big O n squared. So when we see the n here, that's mean the number of the data we have. So the typical example for the big O n, we can think about we try to search an array for a match value. So here we have a static array, A. The size is capacity cap. So if from this cap, that's mean in our array we have cap element. If we want to looking for a specific value, for example, we say this value is match this value variable. from this array, if we want to find if I have this value or not, of course, you know we need to write a for loop. So we have I index equal to 0, index less than cap. So every time, actually, we just try to find the value from the index to see if that equal to the value we're looking for. If they match, you see we break from the for loop. So then you see here, according to the index value, we can know we find the match value or not. So this one, actually, we call that the runtime is n, because you see here we have a for loop. We try to looking for a match value. If we are not lucky, the match value actually is at the end of your for loop. For example, maybe this matching value is about the second half in your array. We almost need to run for I equal to 0, I less than cap. We need to run cap time to see if we find the match or not. Yeah, if we are not lucky, actually the value match is at back end of the array. And also on the other hand, maybe we are really not lucky. We even didn't find the match value. So that means actually you go over the for loop from 0 to cap. So here the cap is the n we represent for. You finish this for loop, you still didn't find the value, right? So you see you compare n times. So right, sometimes we are lucky. Maybe the first one we find that. Maybe at the middle of the n we find that. But no matter what, you see here, averagely, on average, you see, remember, big O represent the average. Okay, average, no matter how lucky we are, we kind of like the average, we can say in the middle of somewhere in the array, we find the value. So that's half n. But one thing is also the big O notation, we don't care about the coefficient. So that's the big O n. So sometimes here we're using the example, say searching an array for a match value. But a lot of time, as long as you have one for loop, you will have your big O is n. Does that make sense? Right, so that's the first big O notation I want to show you. The other one, a lot of time we use that's a big O n squared. What is n squared, for example? For example, we sort an array from low to high. In COMSC210 we show you a couple different sorting algorithms. We have bubble sort. We have insertion sort. So all those sorting algorithms, basically, they are n squared. So here, I may not be able to review all the sorting algorithms. So now here, I just show you. We call that the nested for loop sorting. So you can see here, actually, you have the first for loop, I equal to 0, I less than the cap. So then you see here, that means we start using the first element. Okay, so quickly to show you what does that mean. That's here, you see, we start from I equal to 0. Actually, with outer loop, using this one for the target value. So then you see j equal to I plus 1. So that's why j will be the next one. So always start from j equal to I plus 1, right? So we want to from low to high. So that's why we just compare. If the value I greater than the value in j, so then we swap. Otherwise, we just do nothing. Then continue inner loop. We go to the next. So that's why here, the nested for loop, the outer for loop, we start from I equal to 0. We do one by one. So every time the outer loop, you have one inner loop, j start from I plus 1. So start from the next one until the end. Whenever we see any value in the j to the last one smaller than I, so we just swap the value. So that's why we can see each iteration from the outer loop, we will have the AI will have the lowest value. So then the next iteration, we just move I plus to the next one. So that's why you see here is we call the runtime averagely will be n squared. So one thing is you will see here, we have one for loop, we have the second for loop. So usually when you see you have a nested for loop, 2-layer for loop, the runtime is n squared. Okay, so that's a quick preview about the runtime. So why I need to talk about the runtime? So you can see we have the two different algorithms. We have runtime n and runtime n squared. So one thing is you can see here, I just want you to focus on these two columns. So this table actually you see in first week. Okay, so here we just assume, you see n equal to 100. And also we assume usually your computer, the process time, your CPU process is gigahertz. On the other hand, each operation, they will take 1 nanosecond. That will be 10 to the negative 9 seconds to complete. You see, if your n just 100, 1000, honestly, no matter it's n or n squared, their runtime are less than 1 second. So do you really care? They are really run very fast, right? So I don't really care. But here is we say n equal to 1 or equal to 1000. It's not big data. Big data we say is what? Big data is the data you process is 1 million or 1 billion or even more. So then we see the big data will affect how much. Okay, so if your data is n, for the linear algorithm, big O n, your runtime, okay, still less than 1 second. Even you become 1 billion data, you can finish in a couple seconds. Okay, so the linear data is still fine. But linear data, sometimes we want to do the searching. But how about we want to do the sorting? When you want to sort 1 million data, you can see here your runtime actually will become n squared. So we have 1 million squared is 10 to the 12 power. So then you can see here to process that many data in n squared algorithm, you will about like runtime is 16 minutes. Have you ever think about your runtime is 16 minutes for your code? Do you really want to search on the internet? You just want to Google something, then take 16 minutes to give you the result. Right, before that's slow. But now you can see here, when you type some keyword in the Google, less than 1 second they give you a result and a lot of link to provide you. So that's only for the 1 million data. So then we see 1 billion data. If your runtime efficiency is n squared, you need 31 years. Oh, you guys even younger than this age to finish the searching. So that's what we show you. You see your algorithm for the small data, it doesn't matter. Okay, no matter how you write your code, how inefficient your code is, it doesn't matter. But when you have your big O, when you have big data situation, your algorithm actually affect a lot your runtime. So that's what we call the big data. So that's why when we handle the big data, we really need to be careful about our algorithm. So moving forward, actually from this week, we will start talking about one big data application. Actually, this one compared to the big data we talked about earlier is still not enough. You see, we need to talk about big data is 1 million or 1 billion data. But actually, we are good enough. Actually, our DVC scheduling since year 2000 to now, we about have over 85,000 section information. So that's why here, because when in this application, we want to show you, you will start from your algorithm is n squared runtime. Then you will see, oh, that's really slow. Some of your program maybe need to run few minutes if you run i3. So if you are i5 computer, maybe couple minutes. If you have i7 computer, maybe right, few seconds you can finish. But we start test, feel about the big data. So this week, we will start processing a text file. So this text file is have all the course section information for DVC start from year 2000.